Well, let's continue our discussion about direction cosine matrix. So we said that there are different methods to describe the orientation of a body, and one of the fundamental methods, or the fundamental method to describe the orientation of a body, is using direction cosines. Direction cosines are very intuitive, and we do understand them because they simply describe the cosine of the angle between the body frame and the inertial frame. So now our goal eventually is to describe, because this direction cosine matrix changes with time, right? Because it changes with time, our goal is to find the rate of change of this direction cosine matrix. So because if we have, if we know how this direction cosine matrix changes with time, and if we know the initial condition, then what happens is that we can always compute the current initial direction cosine matrix. Makes sense? So we have the initial condition, we have how this direction cosine matrix changes with time, and therefore at any time we can compute direction cosine matrix. So this is our goal. So if I have a differential equation, DE differential equation, where knowing the initial condition, we can determine C for any desired future time. Now, what we have here by now was we had described the any vector, an arbitrary vector in body frame and then in inertial frame. We have related the time differentiation of that vector in body frame and the inertial frame. We know that if B is, and then if omega is our angular velocity, the body's angular velocity described in body attached frame, so B's are unit vectors in body attached frame, then we can relate how we differentiate B in N frame, in our inertial frame, to how we differentiate B in body frame. And in this case, because B is the unit vectors in body frame, so it's fixed. If it's fixed in both magnitude and direction, therefore the first term goes to 0. Therefore, we only have dB dt in N inertial frame being equal to omega cross B. And then for us, it is always simpler to think of our operation in the form of matrix operation rather than cross product. This is easier for me. So the way we do it is you can show that basic linear algebra. You can show that if you define your a skew symmetric angular velocity matrix in this form, then you can describe this time differentiation in matrix form. So you say it is omega. Now in this case, omega tilde is a matrix, is this skew symmetric matrix. So all we have done here, just pay close attention, we have not changed the physics. So all we have done is we have stacked these angular velocities so that we form this skew symmetric angular velocity matrix. We're not doing anything else. So it's about math. So once we have that, so we are here. Now, again, remember, our end goal is to have a differential equation to describe the direction cosine matrix. So, okay, if you recall, again, this is how we related the unit vectors in body and inertial frame. B was equal to C. C again is our direction cosine matrix, N. So what we do here is, because we are interested in time differentiation, so we differentiate both sides. So this is, we already know how we relate the unit vectors in body frame and in inertial frame. Then we differentiate both sides. differentiate left hand side and differentiate the right hand side. Now, because we have two terms on the right hand side, simply product rule applies. We have two terms, but one of the terms goes to 0. Now, why does it go to 0? Think about it for a second. Again, we are differentiating a set of fixed unit vectors, or set of fixed vectors in both direction and magnitude in this frame. So this goes to 0. So we end up having these two relationships. We have this star, we have double star. What we are going to do is we substitute these two relationships into equation 1, and now simplify that and you get a relationship that you're looking for. A relationship, a differential equation that describes how the direction cosine matrix varies with time. So C dot on the left hand side, and we have minus omega tilde C. And this is all we are looking for, because we have now a first order differential equation. As soon as we have initial condition, we can solve this differential equation for any future time. We can, from this equation, we can determine our direction cosine matrix for any future time. At any future time, we can determine the orientation of body frame with respect to inertial frame. So, and then you simply, if I'm just dropping this square brackets for clarity of notation, and just use this double underline. So C dot is equal to CT omega t. So I'm changing the order of this matrix product. I'm also replacing omega tilde with capital omega, which is again simpler. There is no reason, it's just simpler to write it in capital omega form. So this, if you look at this first order differential equation, you should have already seen this simple first order differential equation in your basic second year differential equation course. And this is simply, we can simply C dot is dc dt, and if we integrate both sides, we get ct equal to c0 multiplying e to the integral 0 to t, 0 to time, desired time, omega t dt. So because the solution of this differential equation is simply in exponential form, appears in exponential form. And if your goal is to solve this differential equation between t and t plus delta t, you simply get c at t plus delta t equal to ct, and in this case then ct becomes your initial condition, and exp, short for exponential, t to t plus delta t omega t dt. All right? So we have simply solved this first order differential equation and solved for C. So at least mathematically, analytically, now we know that how we can compute C at time t plus delta t if we know C at time t. And this is I'm going to further discuss in my next lecture. All right, to summarize, our goal was to find a differential equation. Our goal was to find direction cosine matrix at any desired time. So, and I know that if I have a differential equation in terms of direction cosine matrix, and if I have initial condition, I can compute our direction cosine matrix at any future time. So I'm going after that differential equation. So once I have that differential equation, knowing initial condition, we can always solve this differential equation and compute C, our direction cosine matrix, at any desired time. Email me if you have any questions. My email is available on About page, and I'll see you next time.